Okay, so let's look at this topic of catalyst or catalysis. So catalysts are very important in chemistry. And as you can see here, the definition of a catalyst is that it's a substance that increases the rate of a reaction without itself being consumed. So basically, if you compare the rates of an uncatalyzed reaction to a catalyzed reaction, what you'll find is that the catalyzed reaction will proceed at a faster rate. And this that you see on the screen is somewhat of an explanation as to why that happens. Because basically, what a catalyst does is that it enters the reaction to provide a different mechanistic pathway of lower activation energy. And basically, if you lower the activation energy of a reaction, then basically you'll have more molecules having at least that activation energy, and therefore you have the faster rate of reaction to form products, right? So as you can see here, this is the uncatalyzed reaction energy diagram, and this is the catalyzed reaction energy diagram. And as you can see in the case of the catalyzed reaction energy diagram, the activation energy is lower, which means that the reaction rate will be faster. And one can see that to be the case if you look at the algebra of this equation here, right? So here we have the activation energy. And you can see that the lower this value is, the higher the K value is, all right? The lower the activation energy, the higher the rate constant. And the higher the rate constant, the higher the rate. Because remember, according to the rate law of any reaction, rate is equal to the rate constant times the concentrations of the different reactants raised to their respective orders. So therefore, once K increases, the rate of the reaction increases, all right? So as stated here, as the activation energy decreases when the reaction is catalyzed, the rate constant increases, all right? So that's the reason why the rate of the catalyzed reaction is greater than the rate of the uncatalyzed reaction. That is because when you compare the activation energies, the activation energy of the catalyzed reaction is lower compared to the activation energy of the um, uncatalyzed reaction. Okay, so there are two main types of catalysis. You have what is known as the heterogeneous catalysis, where the reactants and the catalysts are in different phases, and there are a couple of examples of this, some of them industrial, such as the Haber synthesis of ammonia, the Ostwald process for the production of nitric acid, and catalytic converters. And then we have homogeneous catalysis, where the reactants and the catalysts would be in the same phase, and usually that's a liquid phase. So you have acid catalysis, base catalysis, and others. So let's look at this diagram here, which is basically a pictorial representation of the Haber process. The Haber process reaction, let me see if I have the equation here. Okay, so here's the equation. It's a reaction between nitrogen and hydrogen to form ammonia. If you mix nitrogen and hydrogen together, the reaction will take a very, 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 very long time. If you do this in the presence of the suitable catalyst, and there are many catalysts that are available, but in this case, we're looking at this solid catalyst, which is basically a mixture of iron, aluminum oxide, and potassium oxide. The reaction will proceed at a faster rate. And in this particular case, the way this works is that the molecules will end up attached to the surface of the catalyst, right? The term for that is adsorption. Let me write this down so that you don't confuse it with absorption. Adsorption, which is ADSORPTION, adsorption, right? Adsorption is what happens when the molecules cling to the surface of the solid catalyst. And then what happens is that the atoms basically separate from each other in the molecules and move along the surface and then come into contact with the other reacting molecules to form your product. So that is what is being demonstrated in this diagram right here. All right. Let me go here. Okay, another example of this is the Ostwald process, where in this particular case, you have a reaction between ammonia and oxygen. Again, if you just mix ammonia and oxygen together without any catalyst, you'll be waiting a very long time for this reaction to take place. If you add a platinum catalyst, which is demonstrated here in this particular setup, then you're going to end up with the products which would be nitrogen monoxide and water. So this is basically how it is done in the lab. And what you see here is a picture of the catalyst that is done in a more industrial setting to produce larger quantities of the NO. That's important because the NO will react with oxygen to form NO2, and then the NO2 will react with water to form nitrous acid and nitric acid. So this is used as a the industrial production method for manufacturing nitric acid and nitrous acid. Okay, we also see heterogeneous catalysis when it comes to catalytic converters in your motor vehicles, right? So as you should know, when fuels are burnt, they produce products which are basically pollutants, carbon dioxide and some other products such as sulfur dioxide and so on, right? So basically, and carbon monoxide, which is of course poisonous. So basically what these catalysts does is that they convert the harmful gases like carbon monoxide into carbon dioxide, which is less harmful, and water, right? So the catalytic converter is made up of different materials, which allows for that reaction to take place. Sometimes you have other gases like nitrogen monoxide and nitrogen dioxide. Again, those are converted to less harmful materials using catalytic converters. We can also see catalysis occurring in biological systems. There are a group of compounds, proteins basically, that exist in biological systems known as enzymes. And what they do basically is hasten or increase the rate of the breakdown of certain biomolecules, which in this particular context, they're known as substrates. So this is just one example. Well, this is a hypothetical example where you have the substrate. And the thing about the enzymes is that they have a particular unique shape which allows for the molecule, the substrate molecule, to fit into it. So that's what is happening as you go from here to here. So this that is formed when the substrate combines with the enzyme, it's called the enzyme substrate complex. And then what that does basically is facilitate the breaking of the enzyme, or I should say the substrate, into more simpler products. And I'm not sure what this example is, but this here looks like, you know, an enzyme molecule, and this looks like the substrate, and you see there's a cavity here. So therefore, the molecule goes into the cavity, fits in there, and it also alters the shape of the enzyme as well. And then eventually what will happen is that the molecule, the substrate will break up to form simpler products. Okay, so this is showing you what happens in most enzymatic reactions, basically compared to the uncatalyzed reactions. So here we have the substrate, here we have the product, here we have the activation energy, which is the difference between here and up here. But in the case of an enzyme catalyzed reaction, you have the enzyme combining with the substrate, gain some energy, then comes down here to form the substrate, which is the enzyme substrate complex, which is actually more stable than the enzyme itself. And then you have a further step where the products are formed from the enzyme substrate intermediate. Now, some kinetics here. The rate of the reaction, of course, can be measured by the rate of change of product over time. And we can, of course, express that as the rate is equal to K times the concentration of the enzyme substrate complex. We can say that because if you look at this here, this peak here is higher than this, which tells us that the second step is slower than the first step. So therefore, the rate is equal to K times the concentration of the enzyme substrate complex, all right? But what is found when you actually do this experiment to look at the relationship between the rate of production of the product and the concentration of the substrate is that as the rate increases, as the concentration of the substrate increases, the rate increases up to a point. And this point represents where all the active sites that are present in the enzyme will be occupied, and therefore this substrate will not be able to react any further. So therefore, basically the rate of production of the products basically remains the same when you get to that point, all right? So that's basically what happens in biological systems, specifically as it relates to enzyme catalyzed reactions. Okay, so that's basically the end of this chapter. The next chapter, we're going to deal with the topic of equilibrium.